And finally, let's consider osmotic pressure. Here's the setup for osmotic pressure. You have a chamber, or a cell. It's actually an osmotic cell. People actually do this. Looks something like that. And here we have a semi-permeable membrane. This might be, for example, a biological membrane. This membrane is semi-permeable membrane is permeable to solvent, and it's impermeable to solute. And let's just put some solvent in here. Let's call it H2O, some water. And we fill this up with water till these are capillary tubes here, till the level in the capillary tubes is about equal, or is equal. And of course you would expect these two to be equal because there's nothing pushing water up or down. So when you first start out the experiment, water on both sides, the membrane is permeable to water, these water levels will be equal. Now say on the right hand side, let's add something that's impermeable, and typically if you want to be biological, let's add a protein. But it could be any solute that is impermeable. Now we look at this and we say, where is water more concentrated? Well, by adding the protein on this side, you've diluted out the water, so water is more concentrated on the left-hand side. A more fancy way of saying that is the chemical potential of water on the left-hand side is greater than that on the right-hand side, because chemical potential and concentration are related, logarithmically, but nonetheless monotonically increasing. All right, so what's going to happen when you put the protein there on the right-hand side? Well, water is going to flow down its concentration gradient from a high to a low. So water now is going to flow down the concentration gradient. So as the water flows this side, this water level goes up to here. And as it flows, this water level goes down to here. So now you have a difference in water levels above the solution. On the right you have a higher pressure than on the left, the hydrostatic pressure difference. And what happens is qualitatively is that this pressure, extra pressure due to this water column, cancels out the difference in chemical potential. So the chemical potential makes water go this way, but now this hydrostatic pressure is making the water flow the other way, and when it reaches equilibrium they balance each other out. The height of this water column exerts a pressure, and this is called the osmotic pressure, which is given the symbol pi. Let's call this, say, compartment 1, and this compartment 2. So at equilibrium, the chemical potential of water in compartment 1 is equal to the chemical potential of water in compartment 2 at equilibrium. So let's look at the chemical potential in compartment 1 over here. The chemical potential of water in compartment 1 is the standard state chemical potential of water in compartment 1 plus RT times the natural log of the activity of water in compartment 1. The activity here, so there's no extra hydrostatic pressure difference here. The activity of water on this side will just be 1. It's the pure substance. There's nothing over here. So in fact the chemical potential water in the left-hand side is just the chemical potential water in compartment 1, standard state. Now let's look at the chemical potential water in the second side. Well, that'll be a standard state chemical potential of water in the second side plus RT times the natural log of the activity of water. Let's assume we have an ideal solution, so I'll just put mole fraction of water on the second side. And then we have an additional component due to this pressure difference here. So I'll call that mu for osmotic pressure. Note that this component will be negative since the mole fraction over here is less than 1 because we added protein, we diluted it out, and that will have to balance out with this extra chemical potential due to the hydrostatic pressure. Let's look at this extra chemical potential due to hydrostatic pressure. How does chemical potential vary with pressure? Well, we know or maybe we don't know, maybe we don't remember, but let's do it this way. How mu changes with pressure at constant temperature is just the partial molar volume. So we integrate that, d mu will be the partial molar volume dt. Let's integrate this from what we have on the left. That's from the water in compartment 1 to the water, chemical potential water in compartment 2. That'll be V, d mu. And we're going to integrate the partial molar volume over temperature. Oh, sorry. What did I do? This should be pressure. Okay, dP. So this will be from the pressure on the left-hand side to the pressure plus the osmotic pressure on the right-hand side. What we have here, this is just regular old water at 1 pressure on the left-hand side. And now we have here water is a lower chemical potential because of the dilution by the protein, but it's a higher chemical potential because it's hydrostatic pressure. We're calculating that extra term for the hydrostatic pressure. Mu of H2O in compartment 2, the difference in chemical potential minus mu H2O in compartment 1. Let's assume partial molar volume is a constant, so this is just BV, osmotic P pressure on the left-hand side plus that extra osmotic pressure minus the pressure on the left-hand side, partial molar volume. So this is equal to the osmotic pressure times the partial molar volume. So that's what the extra stuff is for the hydrostatic pressure over here. This should be a standard state. So what we end up with is that RT times the natural log of the mole fraction of the solvent is equal to minus pi V bar. We'll make our usual assumption of dilute solution, where the mole fraction of the solute or solvent can be replaced by 1 minus mole fraction of solvent in a dilute solution. So this just be equal to minus RT times the mole fraction of the solute, and we did that with the Taylor series expansion, is minus P times partial molar volume. All right, at this stage, we might look at or try to remember what the introductory chemistry equation was for osmotic pressure. It was the osmotic pressure pi is equal to the molar solution concentration times R times T. This is what we got so far, considering equality of chemical potential at equilibrium and the extra chemical potential due to the hydrostatic pressure difference on the right-hand side. So let's see if we can go from here to here. I think we can. This is a plus and a plus, so that sort of cancels out. And remember, and let's just remember that the mole fraction of the solute is equal to the molal solution concentration times the molar mass of the solvent. So if we just put that in, we have RT times the molal solution concentration times the molar mass of the solvent. That's equal to pi times the partial molar volume. Let's isolate pi. So pi will be equal to RT. Now we have M, the molality, times the molar mass divided by the molar volume. Now let's look at these terms in particular. Let's put some units on here. The molality is mole solute per kilogram solvent. The molar mass M is the, we'll put an SI unit, kilogram of solvent over mole solute, kilogram over mole, mole solvent, and the molar volume is the volume per mole of solvent. Because remember, the solvent is the one that's moving back and forth. So if we start cancel these things out, kilogram of solvent, kilogram of solvent, mole of solvent, mole of solvent, what you're left with is mole of solute per volume. Mole per volume is molarity. So this term is just molarity. Molarity times R times T. there is the introductory chemistry equation that was just presented, but we got that by considering chemical potential and the extra contribution to chemical potential due to this hydrostatic pressure gradient. So that's it for colligative properties. I think what else we got here? There we go. 1, 2, 3. So those are the 3 other colligative properties that we have. Now, for the last part of this lecture, we'll do some examples.